All right. We were going over some capacitance and potential related problems, and we ran out of time. So I think I would like to try and address some of the things I didn't cover. So here we go. We got a conductor. It's actually a sphere, but it's hollow. So here we've got this hollow sphere. Let's see if I can keep drawing this here. There we go. And there is a plus Q charge on the outside. And the way the problem is worded, it says a spherical conducting shell has a net charge of plus 5Q. And at the center, there's this single charge. What we want to know is what's the charge on the inside of the shell? So this inner layer right here, what's the charge here? That's what we need to talk about. The first thing to consider is the fact that there is a plus Q right here. So no matter what, we're going to have to, when you end up with a charge happening on this inner layer, it's going to have to be minus Q by induction. Okay? And the reason that's true, if I switch colors here, if we make a Gaussian sphere here, it has to have, that's supposed to be a Gaussian sphere. Inside the hollow conducting sphere, E must be 0. Has to be. We don't have any other choice. So the only way that would work, the only way that the E field measured from just outside that inner edge, the only way a Gaussian surface, so E times whatever that 4 pi, here we'll draw an R there. Let's call it little r squared. It has to equal 0 because it's a conductor. But what that means is Q net over epsilon naught. So the only way that would work is if we have a plus Q down in the middle, that means that this inner edge must be minus Q. We don't have any choice. The sum of them have to be 0, so there's no charges included. So if we were to draw a Gaussian sphere way out here, all we would get, if I can do it, all we would get there is, and let's call that one R2, E times 4 pi R2 squared, that's supposed to be an E, would equal 5Q over epsilon naught. And see, they've already told us that the net charge on the thing is 5Q. The only way that the combination of Gauss's law near the inner edge and Gauss's law on this far outer edge would work is if, due to induction, we end up with a negative Q on that inner edge. Okay? So I hope that one makes sense, but we're applying Gauss's law in a couple of different contexts there. Right in this inner edge here, we would figure out a Gaussian surface and then think about what would happen out here. So between the two, we're saying that because the inside of a solid conductor has no electric field, that means that the Q enclosed must be 0, which means if there's Q down in the center, then we must have an induced negative Q on that inner edge. Okay, I hope that's good enough. All right, so there was another one I meant to talk about. So that was about the conducting shell that was hollow with a charge on the inside. Here's another one. Here's another good one. So I've got this E field here that already exists. There it is. And then down here I've got this conducting, oops, that is a terrible drawing. It's supposed to be a circle. Not much better. But here we have a non-charged conducting sphere. So what happens if we bring this thing inside? Let's move it up there. Let's move it inside. So here's our sphere now. Q has to be 0. We haven't added any charges. But because we put it into an electric field here, I'll draw a couple of the lines. It's going to do like this. There, and like this. There, and like this. There. That's an arrow, by the way. And it has to go in on this side and out on that side. It has to be at a right angle to the surface. All of those things must be true, which means this side has an induced temporary polarity of pluses, and this one has an induced temporary polarity of minuses. We don't have any choice. So as soon as you moved the sphere inside, very, very briefly, some of your electrons in this on the right-hand side, they would redistribute themselves to the left-hand side. As long as you're in the electric field, it would stay polarized. And even though there's no net charge on the inside still, the outside of the thing is temporarily polarized just because you brought it into this electric field. And by drawing the field lines, you can see which ones are plus and which ones are minus. You can see electrons would be drawn over to the left. Or if you want to think about it, you had plus Qs, they would be pushed over to the right. Either way, that makes you feel good. So they would move along the surface like this, the plus Qs, and minus Qs, if they are a thing. So electrons are actually doing that, would go the other direction. All right, so those were two of the three that I didn't get to talk about. And then there's one more. It's not so bad, could be worse. So it's again a conducting sphere. So I've got this big sphere, and it's got a charge. I can draw. I really can draw a sphere. Let me try again. It's got a plus Q on the inside, and there's this point over here labeled B, this point over here labeled A. And here's the question. If I take, so Q is made up of a bunch of individual charges. Here's one of them right there. Wait, let's make it a different color. Let's make it red. Okay, there's a little tiny plus little q. And what I would like to do is move it, oops, dang. I want to move it from B over here to A. Or imagine if I just cut right through and I move this plus q over here to A. I physically do it. So I am actually having to do work to make this happen, okay? Well, the thing to remember about a conducting sphere is it's potential all over the surface. So it's the same potential. So potential at B equals potential at A, like that, which means, and here's the point, even though I'm doing work, the amount of electrical work we did is equal to 0, right? So the delta V is 0. They're equal to each other. Well, just to remind you what that has to do with energy, change in potential energy is charge times change in potential. If there's no change in potential, there's no change in potential energy. It's very similar if we were to think about it from a gravity standpoint. Here's the ground, and I have a block of mass m, and I'm going to pick that block up, and I'm going to put it right over here. Well, what's the change in potential energy due to gravity? It's 0, because the delta H was 0, and we know that delta U equals mgh equals 0 if delta H is 0. So well, I guess that's a delta H, isn't it? There. If there's no change in height, there's no change in potential energy. It's the same story with our charged sphere. It doesn't matter what path. This is path independent. Independent. It doesn't matter what path you take. All that matters is, did the potential actually change? And since the potential didn't change at all, we're located on the surface, it doesn't matter if you cut all the way through the middle of the sphere or took it all the way around. The net electrical work done, the work equals 0. It doesn't matter if you took the path all the way through the middle or you took a path around the outer edge or along the surface. They would be equal to each other and the work would be 0. Now, I did work, but it's not useful work. I didn't do any electrical work. So there was no change in potential, so there's no change in the electrical potential energy. Okay, those were the ones I wanted to cover. I hope that's good enough. Make sure you reach out if you're not clear on any of these.